we haven't started yet, but. So your class participation for today, which is due by Friday, the beginning of the class, and the reason is I know not all of you have computer to bring to the class. So if you have it here, you can do it now and you'll be done. But if you don't have your computers and you do that at home, you have to tune the parameter based on the requirement given in your class participation. All right. So if you dealt with controller before, shouldn't be too much of a problem. And I've given you the equations just to help you, since this is just a class participation. All right. So a quick recap. Okay, you can stop talking and listening to me. Quick recap, PDPID, PD control, PID controller. We will develop the control law, right? So both of these are for set point tracking. If you remember, we could have, this is very loud. Or is it good? I don't know. Is it too loud? No good, okay. So we could have trajectory tracking, controlling, right? Or set point tracking. So we're gonna focus on set point tracking, meaning that we track one point at a time, and if you update, you can follow a trajectory. But velocity and acceleration are not important here, meaning that how fast you're going toward that point in set point tracking doesn't matter. All right. So this is the easiest, basically. You have a point, go there. Right? Okay. So for PD, we have KP, and then that's the position control X minus X desired minus KV X dot. And if you want to design a PID controller, the only thing you're adding that I term, and that will get rid of your steady state error. So if you had steady state error, you will add that term. If not, you will stick with PD controller. All right. For a system, you'll see that PD is enough, so we won't go further from there. Now, what I want you to do is to develop the equation of motion for a single link manipulator dynamic. You should be able to do it without looking at your previous lectures. So whenever you hear single link manipulator, think about, you could have a joint, right? Or you could also have the case of pendulum. Still a joint, right? It's just different. So this basically could go 360. So if you hear pendulum problem or single link robot problem, they are the same thing. All right. So your equation might change a little bit, but because they're sine cosine, it will be the same. If you move around this 360 or 180, wherever. So we're going to stick to this. A few things about the system. So this is a revolute joint. The length of this link is going to be L or L1. And then center of mass going to be R or R1. So this is where gravity is applied. This is mass M1. Your variable is theta1, which means that you can move from here. So again, if this was a pendulum, by the example that we will solve, you will start moving from probably at equilibrium point, right? Or if you had the initial condition, you'll move from your initial condition to where you want to go. Make sense? All right, so what I want you to do is find equation of motion for this. Write that, then we will go and find the controller. So I'm going to give time to everyone. So if you're watching over Zoom, there's going to be a lot of wait time. Homework, you have to code. No simulating, no tools. Remember, we are working on basics. We're trying to learn the algorithm and how to do it. You are the person that will write the tool for someone else. Hopefully. It should be Follow my direction for now. You could also use Lagrange. I'm sorry. All right, if you missed this slide, come talk to me. I'll probably write something in my annotated lecture. All right, so let's not do that for now. So we want to now grab this, go to MATLAB and see how we're gonna code, right? So very simple system. You've already probably modeled it in your homework. Hopefully, anybody, if you have done it, if not, hint, you're gonna use kind of what you're doing here. And from here is going to be weird because Zoom doesn't like to share things the way I want it to share. So if you're using Zoom, let me share screen, but probably is not going to be as what the audience here will see. So copy the two code you had in MATLAB if you have. If not, you're just going to follow me. So you cannot run the program because a few things you need to add. Before we get this, I created a roll call. It should be open. Yes. Go to Carmen, today's module. There's a roll call, but there's 2 questions. You need a password for that. The password is, so go here, open roll call. The password is lowercase roll call. There are 2 questions, answer them and you automatically get points. Just so you know who's in the classroom. You know the password, right? So I'm gonna move from here, continue doing this. All right. So I'm gonna delete the PID so we don't get distracted. Going here.
All right. I'm good. So let's you should take the test first. Where's my Zoom? Okay. Making sure Zoom. Did I write sandwich wrong? The first two times I wrote it, I wrote wrong. This time it's SH. So Zoom is not gonna see this, but let's see what everybody has said so far. Taco is a sandwich. 8 people think it is. Think for yourself. Why would you look at Google? Hot dog is a sandwich. Wow, very cool. Hot dog is not a sandwich, right?
Yeah.
Same as taco, right?
Hot dog is a taco.
Okay, hot dog is a taco.
Yeah, but like, what about connected?
We need to sort this out. You need to design a PID controller to figure this out. Okay, wow, hot dog is very close. Who didn't answer? We have one person can just, well, two, because someone. Everybody answered? We're all good? What do you think? It comes to us. Huh? No. Okay, you're worse than Adrian. You're worse than me. What do you think?
I would like maybe by like definition, but I've never called it a sandwich. So I'm gonna say.
Don't date him. My first debate was, is Google making us stupid? I guess I don't need to make a debate. That's it for debate. But you just proved my point. That's one good aspect of it, but if you just copy and paste, it is helping you not to think for yourself. So depend on how you use it. Thank you. But most people think it's just good. Oh, someone betrayed the class. Okay, now you decide. Now that it is even, you have to think yourself.
I'm still gonna go with false. I've never called it a sandwich. Like I don't think of like when I think of hot
Yes,
dog.
because it said proof.
Clearly, a sandwich is protein.
Because, but hot dog is not, it's just like a bowl.
Sitting in.
Doesn't matter. Hot dog and taco both like a bowl.
Because if you received your hot dog and the bun was broken on the bottom, then you could say, hey, I ordered a hot dog on.
All right, stays for debate. But taco, you sure that is not a sandwich? Right. It is a sandwich. It's not a sandwich. Okay, all right. Let's go back. I'm just gonna make sure that Zoom is going to see this. Now from here, if you're on Zoom and you don't see the plots, it's not my fault because this is weird when you share. Now, let's look at our PD control. So when we looked at our PD controller, the closed loop form, right? So we had the tau, then we had our equation of motion. So now when you're solving this, in your homework, you're going to learn how to use OD45, right? And how to do second order system. That would be a second order system, right? So this is a forward dynamic problem. You have the taus, right? You find the KPKI, then you have the value of tau.
You want to know how your system is moving. What is theta double dot, right? So the problem is here, you have to rearrange such a way that theta double dot is equal to everything on one side. So when you are, so it's kind of a help with your homework, because those of you that try to solve, this was a bottleneck, so I'm assuming will be for others too. I have to remove this so you can actually see it. Hide. So that's your equation of motion with your tau as tau, right? So here, theta double dot is equal to this from your equation of motion divided by the m plus I, right? So you brought that all in one side. From here is just a second order system, use ODE to solve this. Now, if tau is 0, like your assignment, your homework, 0, I don't have any problem. But if you have a PD controller, now tau has to generate torque, right? Now we can write our control law as simple as this. That's how you write control law. Negative Kp, which you will give it a value, theta 1 minus theta desired, minus Kb d theta 1. So these two values come from your OD 45 solution, right? So this is a function for the PD controller, but it has the equation in it. This is a closed loop form because you have the tau, you define tau. Now, if you look back at the model, so introduce the parameters, time domain, initial conditions. So we're going to start theta 1 from negative pi 2, right, at the pendulum hanging, and there's no d theta, so there's no velocity, so it's at equilibrium, is not moving. So if you change that, the solution is going to change. And then you're saving the variables theta 1 and d theta 1 in the vector. Now here, we use OD45 to solve that function, which is a closed form of our model and our controller, right? Now, once we do that, then we're going to plot. This is the plot part. So every time this is called, this will look back here and go and see, okay, what are Kp and Kv? Because I have to solve this equation. Now, how do you find your Kp and Kv? You need some requirement to know where to start. Now, if you look at your class participation for today, I've given you 2 requirements. Ts has to be less than 2 seconds, and then your zeta has to be 1. You remember from the example we solved in the class the other day? So zeta critical damping means that zeta is 1, and then Ts is, what was 4 pi divided by 2 omega or something? You have it in the example. I forgot what it is.
4 over omega.
4 over,
Zeta.
okay, omega zeta or something?
Yeah.
Yeah. So from there, you have the value of zeta, find the value of omega, right? And then guess initial value for Kp. Then I would even say do this. Give your Kv 0. So let's design a P controller for now. So if this is 0, you're now looking at that. So that's just a P controller. So you don't have to change your control law. You can just give this value 0. Now find the value for Kp and tell me what it is, so we'll plot. And it's your turn now. Do the calculation. The goal here is, how do I use the knowledge I've learned so far? Go back to those lectures and find information. Give me a Kp value to start. I'm recording, right? I hope so too. Yes, I'm recording. I am. We didn't mess up this one. Yes.
D theta is
What? So this is reduce the value. So
that's
you're
theta
reducing the
double
value.
dot, not theta dot, right?
D theta is D dot, theta dot. You have to be change your variable. So this is where you need to know how to solve OD. That's problem 1.
Yeah.
Don't worry about it. You
But no, so the equation that's there is exactly what it would be if solved for theta double dot.
it was, yeah, this is theta double dot. Yes. Yes.
Anybody has any value for KP that I can start? That you got it from the equation calculation? No? Do you know where to look to find this information? Because someone is working. Yes. I think for cost participation, did I change the value for, what is the initial state? It's negative pi over 2, right? Cost participation? I think it is, because, so if whenever you want to change your initial value, here's where you change. I think this is for your cost participation. I'm gonna even change this. Let's do this pi over 4. So this is different from your cost participation. So you have to actually do your cost participation yourself. Give me a KP value. 50. Michael's just waiting for a thought. So last class we solved an example. Go to that. That's where you want to start your initial guess. So that's not going to be your final solution, that's the initial guess. Start. Right when all you on the right side. Go to the example last class, that's right there. 4 over sigma omega n is here. 4 over beta omega is your CS. I'm going to use 50. Someone said 50. I'm going to save this and then draw. Let's change forward. It's going to take a little. Ooh, look at that. So that's the animation part. What does that tell you? It's definitely not stable, right? So from that, we don't ooh, look at this. Definitely not. So it's bounded, but it's not stable. So let's see if we can do something here. What should I do? I have lots of overshoot and oscillation. What should I do? This is the control, understand control. We moved from robotic. Now we're in the control because we're trying to control this robot. What would you do if this happened? I would decrease it. I'm gonna go, usually I go half, see what happens. Let's see what 25 brings to me. You have to do this. So that's why PID controller still oscillating, but it's not as crazy as that last one. So PID controller is easy to program, easy to write, but not easy to tune. Depending on what method you use, still going crazy. So let's say if I give this, bring it lower. Top of that, 10. So I'm just using, oh, no, I cannot write this. I'm still using a P controller, right? I want to know if a P controller would be enough. If not, then I'll have to move on and add D. I have to damp those oscillation a little bit. All right, so less frequency, but still not damped. It's time to give some KV. So let's say this was 1. Save this. You see the difference? I added a little bit of damping and drastic. So this needed to have, if this needed to be a PD. You could go your P, like
below 10, close to 1, but when it's close to 1, what does it mean? Kind of 1-to-1 ratio, right? So you're not changing your signal as much.
So what is happening here? So we got a lot better, right? So where should we go from here? What does this graph tell you?
Whatever the word, there's an error between it and value of
So we needed to go to 0, right? We're very close to 0. We don't go to integral yet. Why? We still have something else that's not right. What's not right?
Or that might be
Well,
the overshoot.
the overshoot, what was your zeta? 1. Zeta 1 is critical depth, right? It has to be, that's what you want to achieve, right? Go up, right, under. Let's change. If we can get to that, if we can make it to look like critically down, then we still have a steady state error BI. All right.
So these usually are, yes,
where are you defining KP?
here. In my PD controller, I wrote KP equal to values. Where you define your first guess, you were supposed to use those equation you had. I heard 50, I put 50, and then it's like too much. And I'm backing down by looking at the performance. So I'm gonna make this 2. Oh, cannot run that, I have to run this, but that's your code. All right. Started from negative 45. Well, almost what I want. So I'll try increase my KV a little because I could get rid of the overshoot. Increase KV a little if I couldn't get rid of my steady state error, then one way is to add some I. But if you were asked to design a PD controller, you cannot add I. You have to play with these two until it matches. So I think if I hold that and run, it should be good. I'm gonna make this a 3. Let's see if that works. Yeah, it will. Did it save? I'm not sure if it saved it. Still not, right? So then I have to design a PID controller. You can still increase the values of your KV. You might be able to get rid of that. If not, let's see. And design a PID controller. I'm going to delete this one, delete that one. And then for your PID controller, we can assume that integral part is going to be like a theta or a fixed value. So just integrate over time. So if I run this, so same thing, I just changed the control law. Okay, now what's the problem? So we got rid of a steady state error, right?
It's still oscillating.
Oh, that's fine. Still, but still zeta is not 1, right? It's very close. So zeta has to be 1. There's another problem. What is your PS? So like that. Greater than 2, right? You have to bring it back to 2. So now you have to adjust the values for KP, KV, and KI to make sure this works. So that's how tuning controller works. Look at the behavior adjust. For your CD, I asked you to work on the PD controller. So we cannot add I. Go use step and see what's your best and closest to get to. If you had a steady state, report your steady state. Your initial condition is different for that example, right? So it's going to be different from the numbers I have here.
All right, submit that by Friday. And then on Friday, we work on course. Awesome.
Is there a way to make-
You can write the equations for it and then calculate KP based on that. But that will be your first guess. You would never, so you want your first guess to be an educated guess. That's how you get it. There are other methods that you can also